Okay, so I'll be explaining my solutions. This is basically an editorial for the AtCoder Beginners Contest 437. I was able to solve from A to F, so I'll be trying to explain my solutions for those problems. The problems were decent. I except from C, like I wasted a lot of time on C, but outside of that, I felt like the problems were kind of straightforward. You had to make some inferences and all. So for A, this is 1 foot is 12 inches. So this is basically just you multiply 6 into 12, A into 12 plus B. So like this was A and B. A was just this and B was basically we were given a grid A, and we had to find the row which has the maximum number of occurrences of elements of B. So for this, like the easiest implementation would be you make a set of all the elements of B. I hope this is visible. Sec. Yeah, you make a set of all the elements of B, and then for every row you just count the occurrences and maximize and then output the answer. So A and B were fairly straightforward. C, I should have solved it easier. The idea is basically this is a typical greedy problem where you have to prove using exchange argument, right? The main idea is like basically for every element we had to decide either to give its contribution to W, basically the weight which will be pulled, or the strength Pi which is to pull. So here, like some common inferences you make, like the first thing what I thought when I saw this was, okay, you sort based on some property, obviously either W or P or a function, a composite function of them, and then you take them. Or the second thought I had was you could maybe binary search on the, since the answer is clearly monotonic. Yeah, since we had to find the maximum, right? The answer is monotonic, so maybe we can binary search on it to find some sort of property. And if it's valid, return that. If the check was easy, but as I found out during my implementation, the check was not that easy. So basically, then the next thing I did was I first tried putting all of them into the W, into the weight, and then started adding PI for pull, but that wasn't working, so I went the opposite way. Basically, if we look at this problem, if we put all of the items of our reindeers in the pull, then obviously we will be able to pull, but there is nothing to pull, right? So here the answer is 0. Now, what we want to do is we want to maximize this answer. We want to pull as many as possible. So for that, our pulling strength must be the highest. At the same time, our weight must be the lowest. So for our pulling strength to be the highest, we want to take out an element from this which will reduce the strength by the minimum, right? So we want to choose the minimum Pi, and at the same time this Wi, it should also be the minimum, right? So this Pi, this I should also contribute the minimum Wi as well. So basically this, and mathematically also it will make sense, like if this is P and we take out I, so this becomes P minus Pi, and this should be greater than equal to Wi, assuming we take out I from our initial P. And once we can rearrange this as P should be greater than equal to Pi, small p, this is capital P, is our total current pulling weight, plus Wi. So this is basically from the total pulling strength we want to take out and we want to maximize as many indices we can take out, right? So the sum of Pi plus Wi should be the minimum. So we basically sort based on this key, we use this as a key and sort it, and we try to take as many as possible. So this was the implementation. Basically, you sort the indices based on Wi plus Pi. This is in increasing order. You get the current total weight, current total pulling power, and the current total weight. And then for every I, we first remove it from the pulling power, add it to the weight, and if it's valid, we increment the result, else we break. Because if this is not possible, then by this equation we can infer that the next case will also not be possible. So this was C. I should have solved this easier, even like the reason I couldn't solve it like as fast as I should have was because instead of like writing this equation down, I was like doing some random guesses, whether to solve it or whether to sort it based on what key and all. Also, the idea that we had to start from max pi also took me some time, but anyways. This is a standard problem, like remove this part and it's a standard problem, then like this won't add much. Basically, we had to find the uh, sum of all the absolute differences of all elements. So for here, for like this idea is also used in the problem F, but basically the absolute difference, one second. The thing with absolute difference is if we want to find some x minus y abs, we can split this into two functions. If x is greater than y, greater than equal to y, then this is just x minus y, right? And if x is less than y, then this is minus x plus y, or y minus x. So here what we do is assume we are trying to find for some element ai, for some ai. If we know the count of elements which are less than equal to ai, then we can just get their sum. If we are to run a loop for every ai, so that would be n square, right? So obviously for n less than equal to 3, 5, it won't work. But here, like in the naive approach, in that approach we will do is we'll count all bj. We count all bj less than equal to y and increment their count. In the less than equal to case, we do this operation. In the greater than equal to case, we do this operation. This is a and this is ai and this is bj. So we do these operations. Now the thing is, for some ai, this is basically if we assume some c and t to be the count which is less than equal to y, right? Let c and t equal to be the count of bj's which is less than equal to ai. So this just becomes ai into c and t. We multiply it because basically this will be like minus some bj1 ai minus some bj2 and dot dot dot. For these are all bj's which are less than equal to ai. So here if we collapse this equation, this just becomes their count c and t into ai and minus there's the sum of all bj's less than equal to ai. And for the opposite case, the equation just flips around, so it becomes c and t. This c and t is count less than y, and this becomes sigma the b's which are greater than. So here we can make the if we sort them based on all bj's, what we can do is we can binary search to find the first bj which fulfills our condition. We can get the count and sum of all the bj's using lower bound. The sum using prefix sum will give us this, and the lower bound value will give us the count. We already know ai since we are iterating on all. So using this iteration and binary search, we can get the answer in n log n. And also we need to do the modular operation since the problem states that. So this is not necessary. This will work without this as well, but I sorted it for some reason, no idea. This is prefix sum. We are building the prefix sum on b. Values can be in long. Lower bound, we get the count less and count greater than equal to. Since lower bound gives the greater than equal to index, so LB would be the count less. And based on the indexing, we add the values in the current variable and we mod, and then we mod add it in the total result and mod. So this was D. E was fairly interesting. E I think took me the longest. If we are discounting G, which I couldn't solve. So here E, basically I feel like the difference in people who solved this and who weren't able to solve this was the fact that if you interpret this as a tree, it becomes like way easier to solve. Like if I interpret it as a tree or some sort of automaton, it becomes way easier to solve, right? Because of the problem is basically stating that we have a sequence of arrays, right? Yeah, we have a sequence of arrays, and the array ith array, the zeroth array is an empty array, and the ith array is built by doing this operation. Basically, if this is the ith array, it's built by going to the second array and then appending 2 in front of it recursively. So here the total, if we were to like naively build all these arrays, the total size will be, or in the worst case, it can be n square, which won't work for n less than equal to 3, 5. So we have to do something different. Here we can see that we are doing this thing, right? At some index I, we are appending this sort of thing. So if we are to draw like the only reason why I even started interpreting this as a graph or a tree was because like I just drew some examples, and there you can see that you are at some array, you append something, some character, let's say not a character, some number, oh my god, append some number x, then you go to some other array with x at the end, and this is, let's say, this thing. So here you can see that this is a state, this is a transition or an edge, and this is another state, right? And states are more or less vertices. So here you can interpret this as a graph. First I started interpreting it as a graph, and here like I did some testing, I did some coordinate compression which wasn't required, but that basically allows us, like if you do some testing, you see that the graph which will be built will be a tree because of this constraint xi less than equal to I, which means the edge is coming from like a ancestor, a previously existing node. So like if I were to give an example for this, so let 0 exist, from 0 we add the character 2 and number 2 and we go to 1. From 0 we add a number 1 and we go to 2. From 2 we add a number 2 and go to 3, my bad, go to 3, and from 0 we add a number 1 and go to 4. Now what we had to do is we had to print a sequence, and we had to sort these 1 2 3 4 1 to n indices such that the string which is terminating at there, like if the corresponding, not string, the array, the corresponding array for 3 is 1 2, right? So the array which is ending at that said node follows this property. Basically we want it to be lexicographically smaller than the right array, and if it's not smaller, if it's equal, then we want this to hold true. Its element, its node number, its node should be smaller. So once we make this graph, we can, like if we assume, if all of these weights were distinct, then we can just do a sort of simple Dijkstra or DFS and get the result, right? If let's say this were, for us, currently assume this to be 3 and this to be, let's say, this to be 5. So here what we would do is we would go to, from 0 we would go to 1 and add 2. So the corresponding string for 2 is 1. Then since we want the lexicographically next smaller string, it will obviously start from this only, right? Since this is the smallest. So for 3 we get 1 and 2. Then this is 5, yeah. Then the next smaller string will be, for 1 it will be 2 and for 4 it will be 5. So here we can observe that we just sort of did a BFS or DFS starting from our start node, and we went to the node with the smallest, this thing, the edge value, right? So this would be the implementation, assuming all of our edge values were distinct, but that was not given to us in the constraint. So here I did some modification to this approach only, which took me some time. Basically an observation here is like, assuming if, wait, I'll make the graph again for the correct values. Yeah, so this is 1 and this is 3. So now all of the node values are, for 1 it's 2, for 2 it's 1, for 3 it's 1 2, and for 4 it's 1 as well, right? So here when we start at some node, we look at the children. Here if their edge values are same, we would want to iterate them in the order of their node values as this constraint stated. Yeah, this one. So what we can do is, we know we have to do this, right? In case of similarity, we have our first criteria of sorting is the edge weights. So first we sort based on the edge weights, and if edge weights are same, then we sort based on the node numbers. So this is basically this idea, this priority was the basis of my solution. What I did in my implementation was, Yeah, when you're at a node, first of all, yeah, this thing, you will not be at a single node, you will be at a set of nodes, right? So here, another the set assumption, the set idea came to me because like if we assume here, let's say two and this, let's say this was not three, this was five and this was three instead. So when we have visited two and four to get our answer, right? The smallest string. We have already visited two and four. So now from two, the next smaller string would be 3 since lexicographically it's 1 2 and its number is smaller, 5 is also 1 2 here, and yeah, 3 is also 1 2 and 5 is also 1 2. So after this we would want to visit 3, right? But if we had done a naive DFS based on where we just visit, we use a node as a indicator of where we are at, then only this node will be visible to us, 5, which is incorrect since we would want to visit 3 after this, visiting 2 and 4. So here to accommodate this, instead of sending a single node in the DFS call, I sent the current smallest node. So first of all, you and these will be sorted in the increasing order. So first of all, we push them in the output vector, and then for every outgoing edge, we add them in a, basically we create a map. We create a map, and the map is basically, it stores the weight and the nodes which have that weight, and the children, actually not nodes, and the children. One second. We will create a map where the key is the weight and the value is the set of nodes which have that corresponding weight. So using a regular map allows us to iterate in increasing order of weight, and once we get the set of nodes, we sort them in increasing order so that we can fulfill this criteria, and then we pass this in the DFS call. So this made the implementation fairly straightforward. At a DFS call, we have a graph, obviously, which was constructed. We have our output vector and we have the current set of nodes. For every node in the current set of nodes, we first push them in the output vector first, and then for every outgoing edge, we add the node to its corresponding edge weight here. And once this is done, for every key pair in increasing order of weight, since we want to go to the minimum weight first, we sort the corresponding nodes in increasing order, then we do a DFS with that set of nodes. We pass V here. So this was the implementation of E. F was interesting. F was basically, if I had to simplify the problem, you are given a set of coordinates on a XY plane, and then you are given two types of query. The first query is you need to update the coordinates of the ith point to the given xi and yi, and the second query is for all the points in a range L to R which is given, find the maximum Manhattan distance. So the distance being defined here is Manhattan distance. Find the maximum Manhattan distance for every point in the range L to R in the given vector L to R with a point the query provides you. So here obviously my first intuition was, okay, point update range query, some sort of segmentary will be applied here. After getting the segmentary intuition, the first thing you try here is you first of all make some rough sketch. One sec. So the generic statement of this problem states, given a coordinate plane, also obviously the constraints would only allow a n log n or n log q solution. You cannot run an into q solution. So here for every query we are given a point xq yq, and we have to find if we have to find any point which is the farthest from this, so we could just maintain the point with the largest x, the smallest x, the largest y, and the smallest y, and based on that we can query all the points, right? But querying all the points is infeasible here. Now, as I stated earlier, this idea was also used in problem D when dealing with absolute values, since Manhattan distance is just abs del x plus abs del y, right? What is this? So here, if let's say we were trying to find a distance of a point which is to the right and to above, so it has a xi greater than equal to xq and a yi greater than equal to yq. So in this case, the Manhattan distance is just this, right? Xi minus xq plus yi minus yq. And then if this point were here, instead of yi minus yq, it becomes yq minus yi. So here we can split our query into 4 sections and we can find the answer for all the sections. Now the thing is, the one thing I was thinking during the contest was, how do I filter the points based on the if it lies in this coordinate with respect to this or this or this or this. But if you think about it, even if we don't filter this and we just naively do this calculation, the result for wrong assumption of the coordinate will just be lesser. Here if these are the 4 equations based on the points. So if xi is greater than xq and y greater than yq, we do this, else we do this or this or this or this. So since we want 4 things, we have to design a segmentary node which can return us all these 4 things. So I created a 2D array xy where basically xy ij will tell I, if I is 1, then our x thing in the function, in this our x will be negative. If y is, if j is 1, then the y thing will be negative, else it will be positive. So this 2D matrix eases our implementation. We initialize it to minus infinity, and this is the combine function, which is just like you take the the combine here is trivial since we have assumed this is our current node, this is our left child and this is our right child. We just want we have our 4 2D matrix here, right? And we have a 2D matrix here. We just want the best result for all 4 values, so we can just combine them naively. There are no checks required, and since our identity element was this all minus infinity, so there are no checks required here. And in the apply, while applying, so we are given it's a assignment update, so we are given some xi yi, and we can just assign them based on our defined rules for the indices here. So this was the assignment, and segment, this was the segmentary template. There's nothing special in that. So after filtering the queries based on the type, if it's update time, we can just update it normally in our secretary. Else for the query, we get our result node. Now the node contains, instead of our result, the node will contain this, right? It will contain the best xi plus yi, the largest, highest. The highest minus xi plus yi, xi minus yi, and minus xi and minus yi. So for this operation, we want to do minus xq plus yq, right? And all of them have their corresponding minuses we want to do here based on the rules defined by this, assuming this to be x, q and yq. So this is just setting those rules, and this is getting the value. This is the value of xi plus yi based on these rules, and this is the value of xq and yq based on these rules. It's opposite, and then we just get the distance and we maximize it. G, I have no idea how to start, so alright, so this was the editorial. I'll try solving G, and I'll maybe add a section after this. I'll add a link if I'm able to get it, but G was a constructive problem and I have no idea how to start approaching this. Even the constraints are very questionable. Alright, so bye.
Take your music move with you. With Premium, you can download your music at higher quality, listen to songs ad free, and play them in any order. Tap the banner to learn more.
एंड सेम भी हो सकता है, अरे यार सेम हो सकता है। टाइम लिमिट ज़्यादा है ना, 3 सेकंड है। और 4 क्वेरीज में हो जाएगा सर। नॉर्मल फैक्ट्री चलेगा आई थिंक सो प्लीज चल जा। Okay. Oh my god, constructive. CCD. Colorful Christmas tree. Christmas tree with bulbs, RGB, and graph light. Graph is a tree, makes sense. और सजी जी से बेबी से भाई क्या है n स्क्वायर चाहिए इसका नक्स पे करना है ठीक है रिमूव करना है the only way to remove is जो remove नहीं हुई है और different color है उसी को remove कर सकते हैं फिर colors ribbons remove करनी है ना बस okay मान लो मैं किसी चीज़ को स्टार्ट करता हूँ तो I can remove or I can not remove तो हो जाएगा, लेकिन स्टेट कंप्रेस कैसे होगी? ये खुद ग्राफ बना सकते हैं इसका, इस ऑपरेशन को क्या खुद एक ग्राफ बना सकते हैं एक्सप्लिसिट? इफ यस देन गुड, एल्स तो दिक्कत है। I hope we got okay. कंप्रेसिव स्टेट में मुझे पता होना चाहिए, लेट्स से ग्राफ बना रहा था। कोई साइकिल टाइप में लगा है, पॉसिबिलिटी नहीं है। फर्स्ट में वो डिसाइड कैसे करूँगा, वो दिक्कत है। चल फर्स्ट आई कैन ट्राई आउट, लेट्स सी। मल्टीपल ऑप्शन और अगर रिमूव मैंने आई करा है तो यूनिकली आइडेंटिफाई भी नहीं कर सकते शायद। डैम भाई, दिस इज नॉट फन। वैसे इसका हुआ होगा। ना हो तो गया जी। डैम, सिर्फ 20 लोग का हुआ है गैस। नहीं 50। भाई यार ये तो पढ़ना पड़ेगा, ये कैसे होगा, मुझे कोई आइडिया ही नहीं है स्टार्ट करने का। एक आई गेस एक ग्राफ बना के उस पर डायग्राम्स टाइप कर सकते हैं इम्प्लिसिट, लेकिन वो ग्राफ किस बेसिस पे बनाना है? हम स्टार्ट तो और कर सकते हैं। काइंड ऑफ ऐसा लगता है जो तेरा ग्रीडी बाइंडिंग कंस्ट्रेंट्स ग्रीडी बैकपैक वाले नहीं है। जी हो गया था।